Measures the position. It's section 2.2 in the text. The primary measures of position that we'll be working with are percentiles and quartiles. Percentile, the p percentile is a data value that, roughly speaking, is larger than p% of the data. For example, the 38th percentile is a data value that is, roughly speaking, larger than 38% of the data. Different texts have compute percentiles slightly differently. They have different ways of rounding, maybe slightly different formulas. This is the way our text does it. I'll do it the way our text does it here. We have a set of 12 exam scores. The first step is to arrange these scores in order from smallest to largest. That's true for any textbook. That would be the first step, to arrange them in order from smallest to largest. So the smallest exam score is 28. Its rank would be 1. The second smallest is 59. Its rank was 2, and so forth. So these are original LAM scores. They're 80, 88, 28, 91, etc. But I just put them in order from smallest to largest. Okay, so there's 12 exams, so that's n is going to be 12. N is our sample size. 65. We want to find the part A. We want to find the percentile for exam score of 65. So 65 is the third score from the largest. So that's rank is number 3. And the number of scores equal to 65 is 1. There's only 1. We do have a duplicate of 88. If we want to compute the percentile for 88, then k would be 2. But for 65, there's only one of them, so k is 1. Okay, so the percentile, it's the rank minus 1 plus 0.5 times k times 100 divided by n. Not all books have the 0.5 times k in them. Some books leave that off, but our book has the 0.5 times k. So you might get slightly differently if you don't put that in there. Okay, so the rank for 65 is 3. So it's 3 minus 1 plus 0.5 times 1, and then times 100 divided by, and the sample size is 12. So 3 minus 1 is 2, 0.5 times 1 is 0.5, so I have 2.5 times 100, which is 2,500 divided by 12, and my calculator here. 2,500 divided by 12. Something's wrong. 2.5. Oh, it's 250. 250 divided by. This is 250. I'm trying to do it in my head here. 250 divided by 12. So 2.5 times 100, 250. 250 divided by 12. About 20.83. I'm repeating threes. And repeating threes. So so it rounds off to about the 21st percentile. 21st percentile. Okay, so 65 is in the 21st percentile. Okay. Okay, so let's do the percentile for 88. That's going to be, it's the same formula, but there's 2 scores of 88, so k is going to be 2. 88's rank is 8. Rank is 8. So if we take the lowest rank here, is the lowest rank for 88 is 8, and then k is 2. So this is going to be 8 minus 1 plus 0.5 times 2 times 100 divided by 12. So 8 minus 1 is 7. 0.2 times 0.5 times 2 is 1. 7 plus 1 is 8. So it's going to be 800 divided by 12. So it's 800 divided by 12. Get 66.6 and repeating sixes. I'm going to borrow the 6, repeating sixes. So it's approximately the 67th percentile. So the scores of 88 are in the 67th percentile. That means they're more than 67% of the data. Okay, more frequently we'll be converting percentiles to scores. So we have the same set of exam scores, and let's find the score that corresponds to the 21st percentile. So this is kind of the reverse process. The only thing is that these formulas are not exactly the reverse of each other. So we may get a slightly different answer, but the formula that we'll use for converting from starting with the percentile and getting the score will be n plus 1 times p over 100. And not all books have the plus 1. Some books have n times p over 100. So like I said at the beginning, there's different ways of computing percentiles, and not all books will agree on it. So we have 12 scores. N is 12. 12 plus 1, and our desired percentile is 21 and over 100. So it's 13 times 21 divided by 100. And this is going to be our rank. This is not going to give us the score exactly, but it'll give us the rank. So 13 times 12 times 21. 13 times 21 divided by 100. 2.73. So we want to take the average of the second and the third, because this is numbers between 2 and 3. So we'll take the average of the second and third exam scores in order, right after they're ranked, in order from smallest to largest. So the second ranked score would be 59. The third ranked score is 65. So we want the average of 59 and 65. So it's going to be 59 plus 65 divided by 2. 5 and 9 is 14. Carry the 1. 1 and 5 is 6. 12 divided by 2. 62. So the 21st percentile is 62. So when we got the percentile for 65, that came out to be the 21st percentile. Although, it wasn't exactly the 21st, it was really the 20.8th percentile. We kind of rounded to 21st. But so because of the rounding, these in part because of the rounding, these processes are not completely reversible. The 21st percentile, that comes out to be 62. Okay, the 25th percentile. Now the 25th percentile, and a lot of texts use that as the first quartile. The first quartile is the number that's more than 1/4 of the data, or 1/4 of the data. It's also called the lower quartile. We'll have our text has a different way of computing quartiles, but if you use percentiles to compute the first quartile, the first quartile corresponds to the 25th percentile, and so we use the same score we used before. It's going to be the rank is going to be n plus 1 times p over 100. So 12 plus 1, and this time it's times 25 over 100. It's 13 times 25 over 100. And 13 times 25 divided by 100, 3.25. So we want the average of the third and the fourth ranked scores. So if we go back to our scores, we want third and fourth rank, so that'd be 65 and 78. Average is 65 and 78, so it's 65 plus 78 divided by 2. 85 is 13, carry the 1, 143, 71.5. So the 25th percentile is 71.5, and some books would make that equal to the first quartile. Well, in a different lecture, I'll go over the way our book does quartiles, which is the method of repeated medians. But if you do it using percentiles, the first quartile would be so Q1, first quartile is 71.5. Okay, 50th percentile, that's also the median. It's also the second quartile, or the middle quartile. And again, we use this formula, n plus 1 times p over 100. So 12 plus 1 times, this time we want the 50th percentile. So it's going to be, comes out to 6.5. And so we want to take the average of the 6th and 7th scores. So we go to the 6th and 7th scores, and that's 82 and 83. So we want to take the average of 82 and 83. Divided by 2, 165 divided by 2, 82.5. So that's the median. And all books would have the same answer for this. It's the 50th quartile, it's the median, it's the second, it's 50th percentile, median, second quartile. There's no disagreement about how to find the median or the 50th percentile. Okay, the 75th percentile. This is also called the third quartile, or upper quartile. And again, we'll have a different way of computing quartiles, but if you use percentiles to compute quartiles, this is how you would do it. So at 12 plus 1, our desired percentile is 75 over 100. So it's going to be 13 times 75 over 100. 9.75. So we want the average of the 9th and 10th. So we go back to our data, and the 9th and 10th are 88 and 89. So it's 88 plus 89 divided by 2. It's going to be 9 8 is 17, 1 8 9 17, 2, 88.5. Okay, so that's the third quartile. Okay. Now there's a graph that's based on the quartiles, and this graph, it doesn't matter how big your data set is. Your data set could be 5 numbers, it could be 100 numbers, it could be 1,000 numbers, but for the graph itself, we only have 5 numbers. So this this graph loses a lot of the detail, which has some advantages, has some disadvantages, but this is called a box plot. The advantage of this graph here is that it's because it loses a lot of details. It kind of is a big help in sort of showing the overall pattern. Now this graph here is very good about it showing symmetry versus skewness. This is a box plot or box and whiskers plot, and it's based on the quartiles. The minimum, you can think of that as Q0, the zero quartile. Then we have Q1, median the same as Q2, Q3. The maximum, you think of that as Q4. So this graph is basically based on the quartiles. We want a box going from Q1 to Q3. So the box goes from 71.5 to 88.5. 71.5 to 88.5. And then the line inside the box is for the median. That's 82.5. And then the whiskers go out to the min and the max. So we have a whisker going down to 28, a whisker going up to 92. And so that's the box plot. And if you look at where the median is, and then look to the left of the median and look to the right of the median, you see that there's a lot more of the box and whiskers extending to the left than there is to the right. So that right there, that tells you it's a left skewed data set. So the box plot is not going to show you how many peaks or clusters. It's not going to show outliers, but it does a very good job of showing symmetry versus skewness. There is a modified box plot that will show outliers, and so I'll go over that shortly. Some of the exercises ask you to give percentages between various quartiles. The quartiles basically divide the data into 4 equal-sized pieces. There's 25% of the data, or 1/4 of the data, is between Q0 and Q1. 25%, or 1/4 of the data, are between Q1 and Q2. Another 25%, or 1/4, between Q2 and Q3. Another 25%, or 1/4, between Q3 and Q4. So the book might ask you, for what numbers are so they might ask you, so what percent of the exam scores are between 28 and 71.5, for example, and the answer would be 25%. Or they might say, well, what percent of the exam scores are between 71.5 and 88.5? Well, that would be 25 plus 25%, or 50%. So anyway, you might see some of those types of questions in WebAssign. Okay, I'm going to get a little bit into measures of spread here. There's a couple of measures of spread that are based on the quartiles, and so I'll go over those now. Later we'll get into some additional measures of spread, but I'll mention the range and the interquartile range right now because those are based on the quartiles. The range is the maximum minus the minimum, so it's like Q4 minus Q0. And in this case, the maximum score is 92, the minimum is 28. And if you subtract, you get 64. Let's see, is that right? Yeah, 64. Okay, so the range is probably the easiest measure of spread to compute. The big drawback to the range is that one outlier can have a big effect on the range. So if the 28 had been a 68, then the range, instead of being 64, would be 33. So that just that one score had a big effect on the range. because if 28 had been a 68, then the lowest score then would be the 59. So a major spread that is not affected by outliers is the interquartile range, and that's Q3 minus Q1. So this is going to be it's 88.5 minus 71.5, which would be 17. That measures how spread out the middle part of the data is. And again, our book uses the method of repeated medians for finding quartiles, which we'll go over in a separate lecture. So you might get a slightly different answer for the interquartile range using that method. Okay, so the interquartile range can be used to identify outliers. Up to this point, we've been sort of eyeballing the graph, and based on the graph, if a number is quite a bit below or above the rest of the data, then we're calling that an outlier. And that's a pretty good way of doing it. It's an intuitive way of doing it. There's a more precise way of doing it using the quartiles. So you want to, I'll go over that now. You want to compute Q1 minus 1.5 times the interquartile range. So Q1 was, I think, 71.5. So this is what we had computed before. Minus 1.5, and we just computed the interquartile range was 17. So it's 71.5 minus 1.5 times 17 is 46. And then we want to do Q3 plus 1.5 times the interquartile range. So Q3 is 88.5 plus 1.5 times the interquartile range, and that's 114. So the outliers would be scores that are either above 114 or below 46. And there's no scores above 114. The only one below 46 is the 28. So again, 28 is the outlier. There's also a method based on z-scores. We'll get into that in more detail later. But a z-score above 2 or below -2 would be moderately unusual. A z-score above 3 or below -3 would be an outlier. So there's 3 methods of computing outliers, or at least 3. One is just to eyeball the graph. Other one is using the interquartile range. And a third method using z-scores, which we'll get into later. There's a modified box plot that addresses the issue of one of the drawbacks of the box plot was that it's affected by outliers. So the modified box plot, instead of drawing the whisker out to the lowest and to the highest, the box part of it is the same. It's only the whiskers that change. You draw the whisker to the lowest number that's not an outlier. So that would be the 59. If we go back to the data set, back to the data set here. The lowest score that's not an outlier is the 59. And there's no outliers on the other side. So this whisker goes down to 59, and then we put a little asterisk, or some books put a little O to indicate where the outlier is. So this is a modified box plot. If you looked at where the median is, there's still a lot more on the left than there is on the right. So it's still skewed left, but it's not as skewed. Doesn't look as skewed as it did before. There's so anyway, that's the modified box plot. There's just to give you an idea of the importance of skewness. A real life example of data that's skewed right would be family incomes in the United States. There are many so they'd be skewed right. So let's turn this the other way. There are yeah, that doesn't work. Still. Yeah, that's good. It's not the. So there's a lot of low and middle income people. So a lot of people in this part of the graph, and then this part kind of stretches out. This is where there's a few rich people so that anyway this probably not the best graph to show that, but so let me just do it like this. So here's a graph that's skewed right. So there's a lot of low and middle income people, and then there's a few rich people. So when you're deciding which statistic to look at, you want to take into account skewness. Some statistics are affected by skewness more than others, and for example, the median income is not going to be affected by skewness, but the mean income will be. So if you look at the mean income, you might that's probably more than what a typical person would earn. The median income would be a better indication of how much a typical person earns. Another comment about the modified box plots. Some books use lowercase o for an ordinary outlier. That would be this 28 here would be an ordinary outlier. They would use an uppercase O for a major outlier. That would be a major outlier would be more than 3 interquartile ranges away from the quartile. It should say this is the median, but from the quartiles. So they would use a capital O for a major outlier, a little o for an ordinary outlier. And that concludes this presentation.